everybody, and welcome to Astronomy Education. My name is Colin Hill, and tonight I'll be talking about stellar evolution, part 1, specifically the Hertzsprung Russell diagram. Next month in part 2, I'll be going into greater detail on how stars evolve and die. Before I start, I'd just like to acknowledge and pay our respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country, and we respect and value their past, present and ongoing connection to the land and cultural beliefs. So just as a bit of a preamble before we get into the Hertzsprung Russell diagram, or the HR diagram, which is probably the most important diagram in astronomy. Just a quick overview on a star's life cycle. So all stars, regardless of their size or mass, they all sort of start the same way with a molecular cloud of hydrogen and helium and dust, which over millions of years collapses and forms protostars. And then the star can take one of three paths depending on its mass. If it's less than 0.08 of a solar mass, it won't be large enough to generate enough heat in the core to fuse hydrogen. So it becomes what's called a failed star or a brown dwarf, and it'll just sort of sit there and slowly cool over millions of years. For a low mass star, so these are stars less than about 8 solar masses, but greater than 0.08. So these are stars like the Sun. They'll burn hydrogen for billions of years, run out of fuel, become a red giant, blow off their outer atmospheres, become a planetary nebula, and then we'll end up with a white dwarf, which cools off over billions of years to become a black dwarf. But no white dwarf has ever had enough time to cool off that much in the lifetime of the universe. And for stars that are greater than 8 solar masses, they go through a similar process, burning hydrogen into helium, becoming a red supergiant rather than a red giant. But eventually they explode as a type 2 supernova, leaving us a supernova remnant and also a neutron star or a black hole, depending on the original mass of the star. So that's a quick overview. We'll be going into a lot more detail next month on that. Okay, so now we'll talk about spectral classes, because we sort of need to know a little bit about this before we get into the Hertzsprung Russell diagram. So this was sort of developed over a century ago. You're probably wondering why the letters are sort of not alphabetical and there's lots of letters missing. Well, originally it was alphabetical and there were a lot more letters there. Originally it went from A through to P. However, the original classification relied on the number of, or the intensity of the hydrogen lines in the spectrum. So an A-class star would have very prominent hydrogen lines through to P. Well, actually P was a planetary nebula, I think, so O would be the least number of hydrogen lines. But sometime later, they decided to classify the stars according to their surface temperature. So when they did that, it reordered a lot of the letters around and they dropped a lot of them out. So that's why we end up with O, B, A, F, G, K and M. And as you can see, an O-class star are the hottest stars. These are the temperatures here. So these are like greater than 30,000 Kelvin surface temperature. All the way down to M-class stars, which are the coolest stars, usually around about 2,500 degrees. And the G-class stars like the Sun, their G-class here, they're about 6,000 degrees. And if you looked at the relative sizes of the classes, you can see that the O-class stars are the most massive ones, and subsequently the largest. These are main sequence stars here, not giants. All the way down to the M class, which are the smallest. Okay, so the Hertzsprung Russell diagram, or the HR diagram, was independently developed by an American, Henry Russell, in 1913, and a Danish man, Ejnar Hertzsprung, in 1905, by studying stellar spectra in clusters. So you can see there was a bit of a gap in time there, but they did develop the diagram independently of each other. So it's an astronomical tool, and it plots stellar temperature, which is equivalent to colour, against luminosity, which is equivalent to absolute magnitude. And it's also called a colour magnitude diagram. And it's useful for studying properties and the life cycle of stars, including mass, luminosity, surface temperature, age, and distribution. So this is the HR diagram. So it's a very busy diagram. So we'll sort of go through it bit by bit. And you can see here on the x-axis the stellar classes that we previously discussed. So O through to M there. And underneath that is the equivalent surface temperatures. 30,000 degrees there, 3,000 degrees here. On the y-axis, we have luminosity. So these numbers here, they're compared to suns, or luminosity compared to the sun. So 1, if you go across the diagram from 1, you'll end up at the sun. So the sun has a luminosity of 1. And then if you come down here, you'll see that it's a G-class star. So if you plot any star in the sky, or in the galaxy, or in the universe, it'll fall onto this diagram somewhere. And when you do plot all the stars, or a lot of stars, onto the HR diagram, you can see that there are groupings. And one of the most prominent groupings is the main sequence. So this is a line of stars from the O class all the way down to the M class, and it's this diagonal line. So this is called the main sequence. So the main sequence are stars that are burning hydrogen in their cores, which most stars do, because most stars spend most of their lives burning hydrogen in their cores. So that's where you're going to find most of the stars. Then we have other groupings. We have the giant stars here, which are stars that have left the main sequence because they've run out of fuel and are burning heavier elements. And we also have supergiants up here. And then down here we have another group of stars, which are the white dwarfs. So these are stars that have no longer burning any fuel in their cores. They're the remnants of low-mass stars. So you can see here these diagonal lines on here as well. These are the solar radii. So you can see here that the stars at the top left part of the diagram are the most massive, or the biggest, have the biggest diameters, and then they come down to smaller, smaller, smaller. And also you can see that the number of masses increases as you go to the upper left as well. So here we have 60 solar masses all the way down to the red dwarfs, or 0.1 of a solar mass. So you can see here that mass sort of drives this diagram. The more massive a star, the hotter it is, the higher the surface temperature, and the further it will move up the main sequence on the diagram. So you can see here the O-class stars, the ones up here, are the hottest, most massive, and most luminous. So here we're looking at 10 to the power of 6 times the luminosity of the sun. So these are stars that are 1 million times as luminous as the sun. All the way down to the red dwarfs, which are a fraction of a solar luminosity. We're looking at here 10 to the minus 4. So these are very, very feeble stars. In fact, there are no red dwarfs in the sky that are visible to the naked eye because of their low luminosity. So you can see there's a few examples here. There's Proxima Centauri and Barnard Star. They're red dwarfs. Then we have the Sun, Alpha Centauri, low mass stars, G class. Sirius A up here is an A class star. Then we get to the more massive stars like Bellatrix, Beta Centauri, and Acamar. Some examples of white dwarfs: Sirius B and Procyon B. And then some of the giant stars here, we have Pollux, Aldebaran, Arcturus, classical giant stars. And then some of the supergiants like Rigel, Polaris, Antares, and Betelgeuse. Or Betelgeuse. What's also apparent on this diagram is the distribution of stars. So you can see as we get up to the more massive stars, there's only a sprinkling of them. And as we go down in mass, the stars become more and more numerous. And that's because low mass stars are produced in far greater numbers than high mass stars. And the other reason there are a lot more low mass stars is they live a lot longer. So even though the high mass stars have a lot more fuel, they burn through it at a much higher rate, as you can see that by the luminosity. So even though these stars are like 30, 60 times the mass of the sun, they're putting out 1 million times as much energy. So for that to happen, they must be churning through their fuel at a much faster rate. And the reason they do that is because of the higher mass of the star. It results in hotter core temperatures because of the gravitational, crushing down of the core, contracting the core, gets the temperature up a lot higher. Higher core temperatures mean more rapid burning of the hydrogen and hence more energy. So the stellar classes, we talked about the O through to M, but these are further subdivided into 10 subclasses. For example, you can have an F0 through to an F9. So F0 would be the hottest, and if you went one further up than that, you'd go to an A9. And going cooler than an F9, you go to a G0. So it's more a fine tuning of the stellar classes. There's also a stellar luminosity classes. So we have there is like Roman numerals. We have running from a 1, which are giants or supergiants. A 2 is a giant. 3 are a giant. 4 is a subgiant. 5 are main sequence stars. All main sequence stars are collectively called dwarfs, even the O-class stars. 6 are a subdwarf, which means they have a low metal content, and 7 are white dwarfs. So as a few examples here, the Sun is a G2V, so V meaning main sequence star. Arcturus is a K03, so a K0 means it's a cooler star than the Sun, and it's a red giant because you can see 3 is a giant star. Sirius A, an A1V, so it's a main sequence star, but it's an A-class star, much hotter than the Sun. And Sirius B, we mentioned Sirius B before, but Sirius B is a white dwarf, the companion to Sirius A. But it's a B1 star, so it's very hot, but it's a white dwarf. So even though it's very hot, it's not very luminous because it's very small. All right, stellar distribution. I sort of mentioned this before, that the O-class stars are quite rare, whereas the M-class or main sequence stars are very common. So if you have a look at this pie chart here, you can see here that 72% of all stars are red dwarfs. And yet we can't see a single one of them in the night sky with our naked eye. In fact, we can't even see any with binoculars. They're so faint. In fact, the closest star to us, Proxima Centauri, which is a red dwarf, is magnitude 13.5, I think, which is extremely faint. You can see here that the G-class stars, like the Sun, make up about 6% of the stellar population. And if you look at the O, B and A collectively together, they make up 0.6% of all stars. And O stars themselves, there's only about 1 in a million stars in the sky are class O. They're extremely rare. But because they're so luminous, we can actually see quite a number of them in the night sky, because we can see these stars at incredible distances. And you can also see there the red giants there, they make up about 0.3%, because the red giant phase is a transient phase between the main sequence and the death of the star. These are burning elements heavier than hydrogen, and when a star's burning these heavier elements, it does tend to use them up a lot quicker than when they were burning hydrogen. So they don't sort of stay in the giant phase for very long, relatively. So that's why there's only a very small proportion of the stars are actually red giants. Okay, so then we'll discuss a bit more about the giant stars. So if you get a star like the Sun, like a low mass star, when it's sitting on the main sequence, it's happily fusing hydrogen into helium, and it will sit there for billions of years doing that. But eventually, it will run out of fuel. And when it does that, the core is now full of carbon. It's full of helium. It's full of helium, which is not doing anything because the core is not hot enough to fuse helium. So fusion continues on a shell around the core. So we have a situation like this. So here's like a main sequence star where we have a hydrogen burning core. But when the hydrogen runs out, we end up with an inert helium core and a hydrogen burning shell around the core. Now this pumps a lot of energy into the overlaying layers of the star, and then it expands because of its extra energy being pumped in. The outer layers expand, and this is what creates a giant star. And as it expands, it cools off as well. The outer layers cool off. So as it leaves the main sequence, it gets bigger and brighter. So it's getting brighter, up more absolute magnitude. But it's also cooling down, so it's moving to the right of the diagram. So it's moving more into the red area. So we have RGB, which is the red giant branch. So a star like the Sun will gradually move off into the red giant branch, continually getting bigger and redder and hotter, until eventually the core, which is continuing to contract under gravity, and as it contracts, its temperature increases. Eventually, it will get to the ignition point of helium, which is about 100 million degrees. So we get the helium flash. This is where the helium in the core starts to fuse into carbon and oxygen. So then we end up with a horizontal branch star. So these are stars in this area here, where helium is being fused into carbon and oxygen. And we end up with a situation like this. We have a helium burning core, and beyond that, there was a hydrogen burning shell above it. When the star gets to this stage, it sort of settles down for a few 100 million years, and it does sort of start to shrink a bit and heat up the outer layers. So it moves back along the x-axis, heating up back more into the orange or yellow part of the spectrum. So we become from an M class to a K or G class star. Hydrogen fusion, as it doesn't last anywhere near as long as hydrogen does. Eventually, the hydrogen runs out in the core, and it becomes an inert core of carbon and oxygen. So we end up with this situation here, where we have the inert core. Beyond that, we have a helium burning shell, and beyond that, a hydrogen burning shell. When this happens, it pumps a lot more energy into the overlaying layers again. Once again, the star expands, cools off, becomes very, very luminous, and comes up to the asymptotic giant branch phase. It doesn't stay there very long. At this point, the star becomes unstable, and it expands so much that it throws off its outer layers into space and becomes a planetary nebula. And very quickly, it goes from here all the way down into the white dwarf stage, whereas it's lost its envelope, and all we have left is the white-hot core of the star. Now, a young white dwarf is extremely hot, so it could be a B or an O class star with a surface temperature 30, 40,000 degrees, but they're not very luminous. So you can see there's the luminosity of the sun here. So a young white dwarf might be almost as luminous as the sun, but as it ages and cools off, it moves along to the probably the G part of the spectrum. But no white dwarf is any cooler than that because they take so long to cool off that the universe isn't old enough yet for any white dwarf to have cooled off any colder than the G part of the spectrum. So it would take about 100 billion years for a white dwarf to actually cool off to become a black dwarf. Right, well, that's sort of what happens to a low mass star. For a high mass star, so we're looking at say 5 times the mass of the sun, they leapfrog the giant phase and go straight into the supergiants because they have so much mass. Once again, it goes through a similar process to this. But once we get up to a 10 solar mass star, it has enough mass to start fusing elements heavier than helium. So it will start burning at a certain point. The carbon and oxygen core will start to fuse and create heavier elements like neon and magnesium. And it will slowly work its way through the periodic table all the way down to iron, or up to iron, I guess. When it gets to iron, iron is the most stable element in the universe. You cannot fuse iron to produce energy. The only way to fuse iron is to put energy into the reaction. So at that point, all fusion stops and the core collapses and it becomes a supernova and promptly leaves the HR diagram, because what you'll have left is either a neutron star or a black hole, which we'll explore in greater detail next month. Now, just sort of show some of the uses for the HR diagram. So one use of the HR diagram is to work out the age of globular clusters, because all the stars in a globular cluster are sort of roughly the same age, because there's no dust or gas in a globular cluster to produce new stars. So all the stars that are produced are the only ones that are ever going to be produced. And if you have a look at the HR diagram of a plot of all the stars in a globular cluster, you'll get something like this. And you can see there that this is the main sequence, and you can see the main sequence stops at a certain point. And there's a knee there, and then it goes off into the red giant branch. So by looking at the point at which the main sequence stops, we can work out the age of a globular cluster. Because as we move down the main sequence, stars live longer and longer and longer. So at a certain point, this is the point where stars are leaving the main sequence. So we know we're looking at here like probably a G0 star. So anything more massive than that have already become red giants and either exploded as a supernova or become a white dwarf. And we know that stars that are of a bit this mass have a certain lifespan, so we can work out that this is the age of the globular cluster, is where these stars have left the main sequence. And so for a G0 star, that's probably about 10 billion years or so. So we can say, well, that's the age of the globular cluster. The other interesting thing in the HR diagram of globular clusters is these little sprinkling of what they call blue stragglers, these hot blue stars here. It was long a mystery of why we'd be getting these hot blue stars in a globular cluster when they all should have long since burnt out and died. And it seems to be the case because the globular clusters are so compact and got so many stars in a small space that we do actually have stellar mergers. So these are stars that actually, I won't say collide, but they'll probably orbit each other, and then in a decaying orbit they end up merging, and this stirs up all of the hydrogen in them, and becoming a bigger star, they sort of reignite and become blue stars. So that's where the blue stragglers come from in a globular cluster. So just a few points of note, or a bit of a wrap up here. Greater than 70% of all stars are red dwarfs. Stars spend 90% of their lives on the main sequence, and that's because hydrogen burning lasts a lot longer than the fusion of any other element. Main sequence stars are burning only hydrogen. Main sequence stars are collectively called dwarfs. And giant stars fuse elements heavier than hydrogen. White dwarfs are the hot cores of dead stars. Brown dwarfs are failed stars, so that means that they're too small for fusion to occur. And high mass stars live fast and die young. So just as a bit of a comparison here, there's the sun, and it will live for about 10 billion years. A 20 solar mass star will only live for 10 million years, so about 1,000 times shorter lifespan than a solar mass star, because it's burning its fuel at a much higher rate. Where a red dwarf will probably live longer than 100 billion years. In fact, the lowest mass red dwarfs, they believe, would probably live for about 1 trillion years. And it turns out that no red dwarf in the age of the universe has actually hit the end of its life. They're so long-lived that the universe isn't old enough for any red dwarf to actually have run out of hydrogen. So we're really not quite sure what happens to a red dwarf when it does run out of hydrogen, because we've never seen it happen. Now, actually, the stellar classes actually go beyond M. They've actually added a few letters. There's a class L, which is cooler than class M. So this is sort of around about 2,000 degrees surface temperature. And it's a mixture of red and brown dwarfs. So sort of the threshold of between a brown dwarf and a red dwarf. We also have T and Y class stars, but these are all brown dwarfs. So these are temperatures less than 2,000 degrees, and because they're so relatively cool, they're radiating mainly in the infrared. And that concludes the talk. Any questions? Yes, Peter.
So the brown dwarf.
Thanks for that, Colin. The brown dwarfs, they're more numerous than any other star. So
we're not sure about brown. Red dwarfs are the most numerous star. Brown dwarfs,
and they're not visible, are they?
Well, some are. They're very difficult to see because they're very small and they're very cool. So
it's infrared or infrared?
Yeah, and mainly in the infrared. So we have actually discovered quite a lot of brown dwarfs, but we're not quite sure how many there are. You're probably right. They're probably the most numerous type of.
So there's not the
object.
dark matter. There's not enough material for dark matter explanation, is there?
Oh, you mean brown dwarfs?
Because you can't see, there might be a lot of them.
Brown dwarfs are candidate for dark matter.
So
is that what you're saying?
I don't think that's likely, is it? Not likely?
Sorry?
Not likely?
No. You need a lot of brown dwarfs to account for dark matter. No. But they're probably the most numerous substellar object out there.
What's the closest to Earth? The
brown dwarf?
Yeah.
I'm not quite sure. It's I think they found one or a few under 10 light years away.
Okay, yeah. Cool, thank you.
The easiest ones to find are ones that are in binary systems. Solitary brown dwarfs are pretty hard to find, I think. Yeah. Any other questions?
Any other questions up there? I'll just take this closer one first. David McKinnon says hi.
Thanks, buddy. G'day, Colin. The sun, a yellow dwarf, it fuses hydrogen into helium. Why doesn't it do it like a hydrogen bomb? Why does it take millions of years to not just explode? With the high temperature and the high pressure.
Oh, why doesn't it blow up?
Yeah.
Okay. I'd probably skip that little bit. All stars are in a state of equilibrium where gravity is trying to crush the star in, and the fusion in the core is trying to blow the star up. And they strike a balance, like an equilibrium where the pressures equalise, and that's where they're stable, right? It's when the balance is upset, like it runs out of fuel, that things happen, and the gravity usually gets the upper hand and it starts to crush the core in. It just made me think too is with the colour of stars is the sun. Everyone considers the sun a yellow star, where it's actually white. It does peak its radiation in the yellow-green part of the spectrum, but it's the atmosphere that filtering out some of the blue light makes our eyes see it as yellow, but it is actually a white star. And the fact you never see a green star, you see all the other colours, but you never see a green star, even though the sun's radiating most of its light in the green part of the spectrum, you don't see it as a green star. And that's because green light gets mixed with all the other colours and produces white light, basically. Just as a side note on that. Okay, any other questions? At the back, sorry.
Yeah, I think you almost answered it with the first question down the front, but the question I've got is, would Jupiter be regarded as a brown dwarf at all?
I think Jupiter needs to be about 10 or 20 times more massive to become a brown dwarf, and about 80 times more massive to become a star. But it's a bit blurred. Where's the line between a giant planet and a brown dwarf? It's I think brown dwarfs, when they're very young, I think they do have enough mass to fuse deuterium for a short period of time. So I think that might be the dividing line between a brown dwarf and a giant planet. But I think it's about 10 or 20 Jupiter masses, something like that. Yeah.
Any other questions?
Was there any online?
Let's have a look. that's about it.
All right, no worries. Well, thank you very much.